In this video, we will explore the force which underlies all non-covalent interactions. Covalent bonds connect atoms within molecules, such as the OH bond in water. In contrast, non-covalent interactions occur between water molecules in this case, as illustrated in this collection of 5. In this image, water molecules attract each other through hydrogen bonds. Non-covalent interactions also occur within very large molecules such as proteins and nucleic acids when parts of the molecule approach each other and get close enough in space. There are many different non-covalent interactions, including hydrogen bonds, dipole-dipole, and induced dipole interactions. Those interactions that don't involve ions are often combined and described as van der Waals interaction. What is the force mediating all of these non-covalent interactions? It turns out there's only one, the electrostatic force, a special case of the electromagnetic force. It's really important when we describe forces to use the term carefully. There are just 4 forces in nature. Those that occur within the nucleus, holding the nucleus together, the strong and weak nuclear force. Gravity, which is the force of attraction between two bodies with mass. And the electromagnetic force, which is the source of all the attractions and repulsions within chemistry. There are 2 components to this force, the electric force, which occurs between all charges, and also the magnetic force, which is between charges that are moving. These coalesce into one force called the electromagnetic force. We're going to concentrate on one special case of the electromagnetic force, the electrostatic or Coulombic force, which is the force of attraction and repulsion between point static charges. The magnitude of the force between 2 charged particles is given by Coulomb's law. The force is equal to a constant times the product of charge 1 and charge 2 divided by the distance between them, r squared. It makes sense that the higher the charges, the greater the force between the ions. Likewise, the greater the distance between them, the weaker the Coulombic force. Additionally, the constant K is very important. It depends on the medium in between the 2 charges. The constant K can also be written as a combination of other constants. One of these is the value called epsilon, the dielectric constant. It describes how the medium in between the charges affects the force of attraction and repulsion between the 2 charges. If the medium is vacuum or air, epsilon is equal to 1, and the charges experience the full Coulombic force. If the medium consists of a polar molecule like water, which attracts and stabilizes the individual charges, you would predict that the charges would exert less attractive repulsive forces on each other. Water has a dielectric constant of 80, which increases the denominator in Coulomb's law, decreasing the forces between the 2 charges. Likewise, if we put in a nonpolar molecule in the medium, like hexane, with a dielectric constant close to 2, there is little shielding between the 2 charges compared to water, so the electrostatic force between them is enhanced. The average dielectric constant inside a protein is about 6 or 7. Inside the protein is more hydrophobic than the outside. So you can see that ionic interactions inside a protein between plus and minus charges would be much stronger than if the same charges were in water. You are familiar with ionic bonds between the monatomic ions sodium and chloride in salt, or between the molecular or polyatomic ions, for instance ammonium and acetate in that salt. Both salts form crystal lattices which are held together by powerful plus-minus interactions that keep the crystal together. We see these ion-ion interactions in proteins such as human lysozyme. We call these attractions salt bridges. They are clear examples of ionic interactions governed by Coulomb's law. A positively charged lysine, which is a protonated amine, and a negatively charged aspartic acid are ions which get close enough to form an ion-ion interaction. The magnitude of the Coulombic force between them depends again on the charges Q1 and Q2, which in this case are +1 and -1. 1 over the distance squared between them, and also the polarity of the environment, which is determined by the dielectric constant in that local environment. The magnitude of the force between partial, not full charges in molecules